Hello my friends and welcome back to the Today Machine channel. By May 2018, Brisbane Sky Tower was well into its structural climb, marking a pivotal moment in the construction of what would become the tallest residential building in Brisbane. This 90-story tower, design soars to approximately 269.6 meters. The developer, Bellside, in partnership with AMP Capital, selected Hutchinson Builders to execute the builder project valued at around 376 million Australian dollars. By this time, the core and perimeter shear walls had been climbing steadily, supported by tower climbing formwork engineered by OM Engineering. Architecturally, Sky Tower has a distinctive triangular core design with gently curving corners, which helps to mitigate wind loading and vortex shedding, crucial for such a tall structure. The curtain wall system comprises high-performance glazing, delivering sweeping views of Brisbane CBD, the river, and distant Moreton Bay. Structurally, by mid-2018, the team had poured significant volumes of concrete, with about 47,000 cubic meters of concrete used across the tower's footprint. The 8-level basement car park, designed to hold 980 cars, had been completed prior to most of the vertical work. One of the engineering challenges was complying with airport height restrictions, since Brisbane Airport's airspace rules cap building height. To address this, a cantilevered structure was installed around level 66, and a special crane was rigged with hydraulic mechanisms so that it could be raised during the day and lowered at night to avoid exceeding permitted airspace limits. Despite its size, Sky Tower was constructed in vertical stages. This staging allowed early occupancy. By mid-2018, more than half the building was reportedly already occupied, helping free capital to fund later construction phases. Amenity-wise, the tower's upper zones, Sky City and the penthouses, were being fitted with a rooftop infinity edge pool, the highest of its kind in the Southern Hemisphere, plus gym, steam rooms, and other luxury facilities. By this point in May 2018, Sky Tower had become a defining feature on Brisbane's skyline, symbolizing both bold architectural ambition and advanced high-rise construction techniques. Westside Place is a major mixed-use development located at 250 Spencer Street, Melbourne. Developed by Far East Consortium, the project comprises 4 high-rise towers ranging from 65 to 81 stories, totaling nearly 2,900 residential apartments, along with luxury hotel components. Stage 1, constructed by ProBuild, included an 81-story tower, approximately 269 meters, housing the Ritz-Carlton on levels 63 to 80, and a 64-story residential tower, approximately 211 meters. Stage 2, managed by Multiplex, added 2 towers of 70 to 72 stories, with over 1,500 apartments, topping out in 2022. A key technical feature is the complex curtain wall facade, designed by Cody Parker, which incorporates 21 different panel types, including bent and folded glass with tensioned cable structures, forming the distinctive architectural profile. The 10-story podium contains more than 3,000 square meters of retail space, multi-level basement parking, and a laneway connecting Lonsdale Street to Little Lonsdale Street. Amenities include rooftop gardens, a swimming pool, sauna, cinema, wine cellar, and recreational spaces. Despite challenges from COVID-19 and supply chain disruptions, the entire development was completed in 2023, delivering a landmark, high-quality urban precinct in Melbourne's city centre. 4 Wellington Place has been approved to a Shepherd-Robson design, with approximately 131,500 square feet of net office space plus retail space. The triangle architecture sits on a distinctively shaped site, creating a standalone scheme and building orientation that fits within the overall development. The construction of 4 Wellington Place in Leeds followed a carefully phased process to deliver a Grade A, high-specification commercial building within the wider Wellington Place master plan. The project began with site mobilization and enabling works, including excavation, temporary works, and preparation of the triangular plot, coordinated to interface with adjacent infrastructure. Groundworks established foundations capable of supporting large, column-free floor plates. The structural frame, primarily steel, was erected to allow rapid construction and flexibility for tenant fit-outs. The external envelope combined stone and bronze tone cladding with floor-to-ceiling glazing, providing both architectural distinction and energy efficiency. MEP systems were integrated early, including a 4-pipe fan coil HVAC system, LED lighting with daylight and occupancy controls, sprinkler protection, photovoltaic panels, and a building management system, ensuring excellent sustainability standards. Internal fit-out progresses in parallel with the structural works, enabling pre-letting to major tenants and optimizing program efficiency. Commissioning and testing of all building systems occurred prior to practical completion in late 2020, verifying energy performance, ventilation, and fire safety. The project demonstrates best practice in modern commercial construction, combining robust structural design, high-quality facade engineering, advanced MEP integration, and flexible floor plate planning. 4 Wellington Place now delivers a sustainable, efficient, and visually striking workspace within Leeds city centre. The construction journey of 7 and 8 Wellington Place in Leeds marked a significant moment in UK commercial construction, delivering one of the city's largest ever office pre-lets. It began with site mobilization and foundational works on the Whitehall Road plot, designed to accommodate approximately 378,000 square feet of Grade A office space over 8 stories. The main contractor, White's Construction, led the build, applying modern lean construction practices. Following groundworks, the structural frame rose rapidly, enabling the large, open-plan floor plates required for the future tenant layout. Facade installation used high-performance glazing and premium cladding, meeting the aesthetic and environmental goals of the development. Parallel to superstructure erection, the MEP teams installed sophisticated services: 4-pipe fan coil HVAC systems, high-efficiency air-cooled chillers, integrated building management systems, and comprehensive sprinkler/smoke ventilation provisions. Custom components, such as prefabricated service modules, accelerated fit-out while maintaining quality timelines. CSD Commercial Services Design Limited, as the interior fit-out progressed, commissioning and verification of all systems ensured compliance with BREEAM Excellent standards. The building was designed from the outset to house over 6,000 civil servants under a 25-year lease by and other key government departments. From groundbreaking to the final finishing touches, 7 and 8 Wellington Place exemplifies the convergence of efficient construction processes, advanced building systems, tenant-driven design, and landmark scale. KOBAX's void former technology is playing a critical role in the construction of Asima Tower, a major commercial skyscraper in Kuwait City. Using its slimline modules, KOBAX replaces up to 35% of concrete within floor slabs by inserting recycled plastic void formers, significantly reducing structural weight and material usage. As a result, designers achieved thinner slab depths, dropping from 60 centimeters to 40 centimeters, while still maintaining strength and load-bearing capacity. The lighter slabs accelerate construction speed, lower overall building height, and contribute to cost savings. Sustainability benefits are also clear. By using KOBAX, carbon emissions are reduced thanks to less concrete production, and the void formers themselves are made from 100% recycled plastic. This innovation supports green construction goals without compromising structural integrity. Park House, located south of Oxford Street between Park Street and North Audley Street, is a large-scale mixed-use development designed by Robin Partington Architects. Park House provides 15,000 square meters of office space, with some of the largest interior office spaces in London's West End, as well as 300 square meters of high-quality retail space and 39 stunning apartments, some with external terraces. One of the major technical challenges was the design and construction of the unique curved glass facade, a torus-based geometry, which required advanced 3D modeling to break down into hundreds of irregular glass and metal panels. Each shell was custom-made and meticulously installed in order, requiring millimeter precision to fit the curved shape. In terms of functionality, Park House includes 9 high-end retail shops, 7 floors of large office space, and 39 luxury apartments with private entrances. The interior uses durable wood and high-quality materials, while high-performance glass and insulation structures were designed to optimize energy efficiency. The floor finishes, glazing, and roof fabrication were executed using a rigorous construction process, coordinated between mace, foci, and seal to ensure quality and performance. The construction of Huntington Apartments, Clayton South, was executed in a series of carefully planned stages to deliver 2 9-story residential towers with 165 apartments. Site mobilization began with enabling works, including ground preparation, excavation for basement car parks, and installation of temporary services. Foundations were laid using reinforced concrete to support the podium towers and landscaped courtyard above. Structural frames combined reinforced concrete columns and slabs, allowing open-plan floor plates for residential units. The podium roof was engineered to accommodate communal gardens, barbecue areas, and pathways, integrating drainage and waterproofing systems. Facades incorporated high-performance glazing and precast concrete panels, installed sequentially with crane-assisted lifts to maintain alignment and tolerances. In addition, Huntington Apartments include specialty disability housing. There are 11 homes specially adapted for accessibility and NDIS livable housing standards, with ceiling hoists, wider doorways, and assistive technology. Unser Glatter house construction in Gross Garau followed a meticulously planned process, with the basement serving as the foundation for a durable and energy-efficient home. The project began with the concrete slab pour, forming a solid base for the subsequent construction. High-strength reinforced concrete was used to ensure stability and long-term load-bearing capacity. Special attention was given to leveling and surface finishing to meet structural tolerances. Following the slab, the basement walls were constructed using precast concrete blocks, assembled with precision to form a robust structural shell. Following the slab, the basement walls were constructed using precast concrete blocks, assembled with precision to form a robust structural shell. The basement floor and walls were then reinforced with additional basement concreting, ensuring continuity and resistance to hydrostatic pressure. Conduits for plumbing and electrical services were integrated during this stage to facilitate future connections. Once the concrete set, thermal insulation was applied externally and internally where required, optimizing the home's energy efficiency and ensuring compliance with German building standards. The insulation layer reduces thermal bridging, contributing to a comfortable indoor climate and lower energy costs. The final stage involved remaining finishing works, including waterproofing the basement, sealing joints, and completing surfaces for subsequent floor coverings. This stage also included verification of structural integrity, alignment checks, and preparation for the above-ground construction phase. Throughout the process, modern construction techniques and precise scheduling allowed for efficient progress while maintaining high-quality standards. The project highlights Unser-Glathar's commitment to precision, durability, and energy efficiency in residential construction, providing a strong foundation for a high-quality, sustainable home in Gross-Gerau. The Quartermile development in Edinburgh utilized BAMECH reinforcement technology to optimize concrete slab construction across multiple residential and commercial buildings. BAMECH is a prefabricated reinforcement system where pre-assembled steel meshes are factory cut, bent, and welded to exact specifications, reducing on-site labor and improving placement accuracy. On-site, the BAMECH mats were positioned directly onto temporary supports or shuttering, allowing rapid installation of floor slabs. Each mat was precisely aligned according to the structural drawings, and connectors were used to ensure continuity between panels. The system significantly reduced congestion within formwork compared to traditional bar reinforcement, facilitating faster concrete pours and improved quality control. After placement, concrete was poured over the BAMECH mats, fully embedding the reinforcement while maintaining the required cover. The prefabricated nature of the system minimized errors and enhanced structural performance, particularly in areas with complex layouts or tight tolerances. The Quartermile project demonstrated the efficiency, precision, and reliability of BAMECH installation, contributing to accelerated construction timelines and high-quality reinforced concrete slabs. The Bellside Bridge, located on the Glasgow-Edinburgh line over the A73, was Scotland's most frequently struck bridge, with over 80 incidents reported in the last decade. The Bellside Bridge replacement involved precise engineering and innovative construction techniques to address Scotland's most frequently struck railway bridge. The new 260-ton structure was fabricated off-site at Lancer Weldon's workshop over 8 weeks, with exact tolerances to ensure seamless integration on-site. During a 5-week full road closure of the A73, 2 cell units and 2 EU decks were installed using a 650-ton crane. Bearings were welded and grouted, and temporary work secured the units to maintain structural alignment. A self-propelled modular transporter (SPMT) was assembled within the compound, capable of rotating the bridge 360 degrees without moving the base, a first application for a UK bridge. Following a 54-hour disruptive blockade, the old bridge was removed, abutments prepared, and the new structure lifted onto the transporter, rotated, and precisely positioned onto the abutments. Backfilling and track reinstatement followed immediately, with alignment and load checks completed to specifications. The bridge deck height was raised to 5.2 meters, eliminating low clearance risks, reducing bridge strikes, and improving operational safety and reliability for trains. The project demonstrates advanced prefabrication, heavy lifting logistics, and innovative SPMT deployment in modern bridge engineering. Precast concrete sound wall systems are engineered to provide durable and high-performance acoustic barriers along highways and urban infrastructure. The production process begins with storage and preparation of materials, including high-quality aggregates, cement, and admixtures. Formwork is then assembled to create the required panel geometry, with reinforcement cages installed to provide structural integrity. During casting, concrete is placed into the prepared forms, followed by consolidation using vibratory techniques to eliminate air voids and ensure uniform density. Surface finishing is applied as required, including texture, color, or pattern treatments to meet design specifications. After curing, post-pour operations such as lifting inserts, dimensional checks, and quality inspections are completed to verify strength, alignment, and finish. Panels are then stored under controlled conditions until ready for transport. Shipment to site is carefully planned to avoid damage, and installation uses cranes or lifting equipment, with precise alignment and secure anchoring on foundations or footings. By manufacturing in a controlled environment, precast sound wall panels ensure consistent quality, structural performance, and long-term durability in service. Keegan Precast specializes in the design and manufacture of twin-wall and filigree floor slabs, using advanced precast technology. The in-house engineering and drafting team develops all elements using a 3D CAD/CAM system, integrating reinforcement, lifting inserts, and embedded services into the digital model. Once client approved, the model is sent electronically to the factory for production. At the factory, panels are plotted onto steel pallets, with formwork, cast-in items such as electrical boxes, and magnetic shutters installed. Edge cleaning and release agents ensure precise tolerances. Reinforcement spacers are positioned before steel is bent, cut, and placed automatically by robotic machinery according to the 3D design. Hidden beam lengths and wall ties are included, and the insulation system is prepared. Plastic-coated spacers maintain the twin wall thickness. Concrete, produced on-site in an N206 compliant batching plant, is spread evenly over the reinforcement and compacted on an oscillating pallet platform to achieve a high-strength, uniform finish. The first skin cures in a heated chamber, after which the second skin is cast and joined with the first. The combined twin wall is cured, demolded, and tilted upright to avoid damage. Completed panels are placed onto custom transport stillages, while filigree floor slabs are loaded directly for delivery. The fully automated process ensures high precision, structural integrity, and efficiency, delivering quality precast panels ready for installation on-site. The 8th Street Road reconstruction project involved a comprehensive upgrade of pavement, drainage, and underground utilities along a critical urban corridor. The work began with site mobilization, including traffic management, signage, and temporary diversions to maintain safe access for vehicles and pedestrians. Existing pavement and sub-base layers were removed using milling machines and excavators, with careful segregation and stockpiling of reusable materials. Subsequently, the project team installed new stormwater drainage systems, including reinforced concrete pipes, catch basins, and manholes. All inverts and slopes were verified to ensure proper hydraulic performance. Utility relocation and protection were carried out in parallel, including water, gas, and electrical conduits, to avoid service disruption. A stabilized subbase was constructed using compacted crushed aggregates, followed by a binder course of asphalt to provide structural strength. The final wearing course was laid using a paving machine, achieving smooth alignment and a high-quality surface finish. Concrete curbs, gutters, and sidewalks were poured to precise levels, with expansion joints and surface treatments designed to enhance durability. Throughout the project, strict quality control measures were applied, including compaction tests, material sampling, and geometric alignment verification. Traffic signals and road markings were reinstated, and street lighting was upgraded to meet current standards. Landscaping and final cleanup completed the project, restoring urban aesthetics. The 8th Street reconstruction improved roadway safety, increased load-bearing capacity, enhanced drainage performance, and extended pavement life. Coordination of phased construction, utility management, and high-quality materials ensured minimal disruption and delivered a reliable, long-lasting transportation corridor for the community. The Michigan Department of Transportation initiated the conversion of the East Junction into a one-lane roundabout to improve safety and traffic flow, starting construction in mid-August. The project featured a fast-track approach, giving the contractor just 21 days of full intersection closure to complete key stages. Subgrade preparation was executed using robotic station control to precisely set elevations and eliminate manual staking. Earthwork removed existing pavement, installed new storm drainage, replaced gutters and conduits, and laid crushed aggregate base at high compaction. Curb and gutter work followed, then asphalt paving of the circulating roadway and central island. Concrete curbs, pedestrian sidewalks, and signage were installed. Traffic control and detours minimized disruptions to adjacent businesses. Upon reopening, the new roundabout replaced the former intersection geometry, reducing conflict points and enhancing safety. Part of broader data which shows the region's roundabouts produce significant reductions in crash frequency and severity. The South Airport Road reconstruction project involved a full upgrade of the roadway, including grading, curb installation, and asphalt paving. The project began with removal of existing curbs and milling of the old asphalt to prepare the surface for reconstruction. Excavators then removed old soil and adjusted the road grade to achieve proper slopes and drainage. A curb machine was used to pour new concrete curbs efficiently, ensuring uniform alignment and height along the roadway. Following curb placement, the base layer of asphalt was paved, and temporary traffic shifts were implemented to maintain safe access. Additional curb removal and asphalt milling occurred on adjacent sections to allow the construction team to adjust grades and build up a stabilized aggregate base. The road was then prepared for the final curbs and sidewalks, which were poured using the curb machine for precision. After completing the final grade and restoring surrounding areas, the base layer of asphalt was laid, compacted, and followed by the top asphalt layer for a smooth, durable surface. Final traffic shifts allowed for controlled reopening as the project neared completion. The South Airport Road project demonstrates a methodical approach to road reconstruction, combining grading, curb installation, and asphalt paving with careful traffic management, resulting in a safe, durable, and fully restored roadway.